A rock barely half a mile across just proved that a lot of what we thought we understood about our solar system might be wrong. Not slightly off, fundamentally wrong. And here's the part that makes this even stranger. NASA wasn't even trying to find it. They were just running a warm-up test. Let me walk you through one of the most jaw-dropping chains of discoveries in recent space exploration history. A story that started with a flyby. Nobody was supposed to care about and ended with scientists tearing up the rulebook on asteroid science. This is the story of NASA's Lucy spacecraft and what it found waiting out there in the dark. First, let's talk about what Lucy actually is, because this mission is unlike almost anything NASA has ever attempted before. Lucy launched on October 16, 2021, lifting off from Cape Canaveral. Its name comes from a famous fossil, a 3.2 million-year-old skeleton belonging to an ancient human ancestor, discovered in Ethiopia back in 1974. That fossil was named Lucy. And just as that fossil gave scientists an unexpected window into the deep origins of humanity, this spacecraft was designed to give scientists an unexpected window into the origins of our entire solar system. The logic behind it is genuinely brilliant once you think it through. Asteroids function almost like time capsules. They haven't really changed much across billions of years. They preserve the chemistry, the physical structure, and the conditions present during the earliest days of our solar system, back when planets were still slowly being assembled out of dust and loose rock. Studying them is a bit like reading directly out of a history book, except it isn't the history of a single nation or civilization. It's the history of essentially everything around us. Here's what makes the Lucy mission genuinely extraordinary. It's planned to visit 11 separate asteroids across a 12-year journey covering roughly 4 billion miles of travel through space. No spacecraft in history has ever attempted to visit anywhere near this many asteroids within a single mission. And the primary targets are something called Jupiter Trojans, a population of asteroids that orbit the Sun in two enormous swarms, one trailing ahead of Jupiter and one trailing behind it, locked into gravitational harmony with the giant planet itself. These particular objects have never once been visited by any spacecraft in human history. Scientists believe they're ancient, leftovers from the earliest formation of the outer solar system, primitive, largely unchanged, and packed full of secrets. That's where Lucy is ultimately headed. But along the way, it had a couple of scheduled stops to make first, and those stops turned into something absolutely nobody saw coming. The first stop was an asteroid named Dinkesh, and this is where the story starts getting wild. Dinkesh was actually added to the mission quite late in the planning process. It wasn't originally on the itinerary at all. Scientists identified it as a potential target simply because Lucy happened to be passing close enough to get a decent look at it along the way. They decided to use the encounter as a test run, a chance to rehearse the exact systems Lucy would eventually need once it reached its real primary targets. Dinkesh was chosen specifically because it seemed thoroughly boring, small, unremarkable, just a half-mile wide rock sitting in the main asteroid belt between Mars and Jupiter, the kind of object you'd use purely to calibrate your equipment before the actual main event even begins. Nobody expected Dinkesh to matter in the slightest. On November the 1st, 2023, Lucy flew past Dinkesh at a distance of roughly 270 miles, close enough to capture genuinely detailed images. The spacecraft was moving so fast that the entire encounter lasted only a few minutes. Back on Earth, the science team waited patiently for the data to arrive, fully expecting routine confirmation photos and not much else. What they got back instead turned out to be one of the most surprising images in the history of planetary science. Dinkesh wasn't alone out there. Orbiting the tiny asteroid was a moon, a satellite, a small companion rock that no Earth-based observation had ever managed to detect. Scientists quickly named it Selim, an Amharic word meaning peace, chosen deliberately because Dinkesh itself translates to roughly the marvelous one in Amharic. Both names trace directly back to the original Lucy fossil discovery. Finding a moon orbiting a small asteroid was already a genuinely notable surprise on its own. Binary asteroid systems do exist elsewhere in the solar system, but they're far from common, and stumbling onto one during what was supposed to be a routine, forgettable test. Flyby was already remarkable, but then more data started coming in, and the science team looked more closely at Selim, and they quickly realized they hadn't actually found a simple moon at all. They'd found something that had never once been documented anywhere in the entire history of space exploration. Selim wasn't a single object, it was actually two separate objects, two distinct rocky bodies gently pressed together and fused into one, orbiting Dinkesh together as a single combined unit. Scientists refer to this as a contact binary, a situation where two separate objects collide extremely slowly without nearly enough force to shatter one another apart, and instead simply stick together, almost like two blobs of dough being gently pressed into a single lump. What Lucy had stumbled onto was the first ever confirmed contact binary satellite orbiting an asteroid. A moon effectively made of two smaller moons fused together, quietly orbiting a rock that literally nobody thought was worth paying much attention to. This had never been observed before, not once, across the entire history of human space exploration. Really, sit with that for a second. We've sent spacecraft past hundreds of individual objects scattered throughout our solar system. We visited the Moon, Mars, Jupiter, Saturn, Uranus, Neptune, assorted comets, and dozens upon dozens of asteroids over the decades. And across all of that combined exploration, nobody had ever caught a contact binary quietly orbiting another asteroid. Lucy found one on its very first flyby, during what was explicitly meant to be nothing more than a practice run. But the story gets even more complicated from there. When scientists dug into the complete dataset from the Dinkesh flyby, they discovered that the actual formation story behind Selim was stranger than anyone had initially guessed. Looking closely at Dinkesh itself, researchers spotted two distinct geological features worth investigating. There was a long trough, essentially a deep scar, running along one side of the asteroid, and there was also a distinct ridge running along its equator, almost like a belt of loose rock that had gradually piled up around its middle. Together, these two features told a genuinely violent story. Scientists eventually worked out that at some point in the distant past, something caused Dinkesh to start spinning far too fast for its own structural integrity. The leading explanation involves something called the Yorp effect, short for Yarkovsky. O'Keefe, Radzievsky, Padek. It's a subtle but relentless physical process where sunlight strikes an asteroid unevenly across its surface and gradually alters its rotation rate over the course of thousands or even millions of years, almost like an invisible hand slowly spinning a top faster and faster over time. Eventually, when Dinkesh's rotation crossed some critical threshold, roughly a quarter of its total mass suddenly broke away entirely. That violent break created the trough. The resulting debris flew outward from the asteroid. Some of it eventually fell back down and formed the ridge along the equator, and some of it drifted into a loose orbit instead, where over time it gradually gathered together and settled into two separate bodies. Those two bodies eventually drifted close enough together to fuse permanently into what we now know as Selim, an entire miniature solar system essentially born from a single asteroid, quietly shaking itself apart under nothing more than the gentle, persistent pressure of sunlight. The research paper describing all of this was published in the journal Nature back in May 2024, and it immediately drew enormous attention from across the planetary science community. Researchers from institutions including the University of Maryland, the Southwest Research Institute, Johns Hopkins Applied Physics Laboratory, and NASA Goddard all contributed to the findings. The overall conclusion was unmistakable. Even the smallest, most seemingly unremarkable asteroids scattered throughout our solar system can carry histories of genuinely extraordinary complexity. And Lucy had proven exactly that on what was supposed to be nothing more than a practice run. Then came the second flyby, and this one somehow turned out to be even stranger than the first. The target asteroid is named Donald Johansson, named directly after the paleoanthropologist Donald Johansson, the scientist who originally helped discover and study the real Lucy fossil back in Ethiopia decades earlier. The naming makes a genuinely beautiful kind of sense once you think about it. A spacecraft named after a famous fossil is visiting an asteroid named after the very man who found that fossil in the first place. But what Lucy actually discovered at Donald Johansson in April 2025 was something that absolutely nobody, not Donald Johansson himself, not NASA's scientists, not anyone at all, could have realistically predicted in advance. On April 20th, 2025, which happened to fall on Easter Sunday, Lucy swept within roughly 960 kilometers, about 600 miles, of Donald Johansson, traveling at a speed of approximately 30,000 miles per hour. The spacecraft was moving so fast, and the entire encounter window was so brief, that Lucy's onboard instruments had to automatically shut themselves down about 40 seconds before closest approach, purely to protect the sensitive cameras from direct exposure to sunlight during the pass. Even with that automatic shutdown built in, Lucy still managed to collect images and spectral data of genuinely extraordinary quality. What eventually made its way back to Earth over the following several days effectively rewrote the existing understanding of this particular rock. Start with the basic shape. Before the flyby even happened, scientists already knew from Earth-based telescope observations that Donald Johansson displayed significant brightness variations on a roughly 10-day cycle, strongly suggesting the object was elongated and steadily rotating. Researchers expected something generally lumpy and stretched out in shape. What they weren't remotely prepared for was the sheer strangeness of the object's actual geometry once they saw it up close. Donald Johansson turned out to be a contact binary too, much like Selim, formed from two separate bodies that collided gently and eventually fused together. But the specific way these two lobes connect to each other is unlike anything scientists had ever documented before. The narrow neck joining the two halves together is shaped remarkably like two ice cream cones placed tip to tip and nested snugly together. NASA's own official announcement literally described it using that exact phrase: two nested ice cream cones floating out in space. The whole structure stretches roughly 8.8 kilometers long and about 4.4 kilometers wide, making it nearly the length of 100 football fields laid end to end. The asteroid itself formed approximately 155 million years ago when a much larger parent object was violently destroyed in a catastrophic collision somewhere out in the belt. The two surviving pieces that make up Donald Johansson today slowly drifted back toward each other under their own mutual gravity and gently merged together over time, not through another violent crash, but through something closer to a slow, almost tender reunion between two fragments that once belonged to the very same shattered parent body. Researchers from the Southwest Research Institute describe the resulting surface geology as strikingly complicated, packed with craters of noticeably different ages and a wide variety of surface textures, all recording a genuinely long history of smaller impacts and gradual changes over time. But the unusual shape turned out to be only the beginning of the surprises. The actual rotation of Donald Johansson is what truly left the science team scratching their heads. Before the flyby, Earth-based telescopes had already measured the asteroid completing one full rotation roughly every 10.5 days. That's slow by typical asteroid standards, but still perfectly normal and unremarkable on its own. What Lucy's close-up data ultimately revealed was that this 10.5-day rotation cycle only told part of the story. The asteroid was simultaneously undergoing a second, entirely separate wobble around its long axis, a tumbling motion that repeats on its own cycle roughly every 26.5 days. Taken together, these two overlapping motions mean Donald Johansson doesn't spin cleanly like a ball or a well-thrown top at all. Instead, it genuinely tumbles through space, more like a football thrown by someone with absolutely no idea how to throw a spiral. Scientists refer to this specific behavior as a non-principal axis rotation state, and it means the asteroid is wobbling through space in a way that's deeply unusual among known objects. Most asteroids eventually settle into a single, stable spin pattern over time as their rotation naturally damps out. This one hasn't. It appears caught in a kind of ongoing physical confusion, simultaneously rotating around two different axes, in a pattern that existing scientific models genuinely hadn't predicted in advance. This particular finding was published in the journal Science on June 18, 2026, authored by Dr. Simone Marchi, Deputy Principal Investigator on the Lucy mission, along with his broader research team. The paper laid out three major unexpected findings from the Donald Johansson encounter. First, the strange dual-axis tumbling rotation pattern. Second, the bizarre nested ice cream cone neck geometry connecting its two lobes. And third, the finding that genuinely took everyone's breath away when the data finally came in, clear evidence pointing toward liquid water that had once existed there, long ago, deep in the asteroid's past. Lucy carries an onboard infrared spectrometer, and when that instrument was pointed directly at the surface of Donald Johansson during the flyby, it detected something remarkably specific: iron-rich clay minerals. Clay minerals simply don't form out of completely dry rock under normal circumstances. They form specifically when liquid water interacts chemically with rocky material over an extended period of time. Finding iron-rich clay sitting on the surface of an asteroid located in the main asteroid belt, an asteroid that formed only around 155 million years ago and measures barely half a mile across, means that at some point in the history of its original parent body, liquid water genuinely had to be present. Not simply ice, not just water vapor drifting around, but actual liquid water existing somewhere inside a rocky asteroid floating in the belt between Mars and Jupiter. To understand exactly why this particular finding matters so much, it helps to think about where Earth's own water actually came from in the first place, which remains one of the biggest, genuinely open questions in all of planetary science. Earth formed relatively close to the Sun in the inner solar system, where temperatures were far too high to allow volatile compounds like water to stick around during the planet's initial formation. So how exactly did Earth end up covered in vast oceans afterward? The leading theory holds that water was delivered to the early Earth through a long series of impacts, asteroids, and comets, originally carrying water from the much cooler outer regions of the solar system, eventually smashing into our young planet billions of years ago. The overall chemical composition of Earth's oceans closely matches what scientists would expect specifically from certain types of water-bearing asteroids. And now Lucy has found direct physical evidence of active water chemistry on an asteroid sitting right there in the main belt. That strongly suggests water-bearing material was genuinely present and chemically active in the asteroid belt, close enough to Earth's general cosmic neighborhood to have potentially contributed to filling our oceans billions of years ago. Scientists went on to compare the clay minerals found on Donald Johansson against similar findings from other previously visited asteroids. When NASA's OSIRIS-REx mission visited the asteroid Bennu, and separately when Japan's Hayabusa 2 mission visited the asteroid Ryugu, both missions also detected clay minerals on their respective targets. But the clays found on Bennu and Ryugu turned out to be magnesium-rich rather than iron-rich, which suggests those two particular asteroids likely had liquid water present for a much longer stretch of time, possibly spanning millions of years, while they were still embedded deep inside much larger parent bodies. The iron-rich clays found on Donald Johansson instead point toward a considerably shorter water episode, a relatively brief chemical encounter, essentially a flash of liquid water activity occurring somewhere inside Donald Johansson's original parent body, before that parent object was ultimately destroyed in its catastrophic collision. And, because Donald Johansson itself only formed around 155 million years ago, making it dramatically younger than Bennu or Ryugu, both of which are estimated at somewhere between 1 and 2 billion years old, it may genuinely represent an entirely different chapter in the broader story of how water moved around throughout the early solar system. These meaningful differences tell scientists that the original parent asteroids behind Bennu, Ryugu, and Donald Johansson most likely formed in different regions of the solar system, or at meaningfully different points in time, and then gradually migrated into the main asteroid belt across billions of years. Each one effectively represents its own separate chapter within the same broader book. Now take a moment and really appreciate what Lucy has actually accomplished so far. It has completed exactly 2 asteroid flybys to date. Both of them were supposed to be nothing more than casual warm-ups. Both of them produced discoveries that were, in their own respective categories, genuinely unprecedented in the entire history of human space exploration. A contact binary satellite never before documented, and a wobbling, double-lobed asteroid carrying the chemical fingerprint of ancient liquid water. And both of these encounters were merely practice rounds, the opening act. The actual centerpiece of the mission, the Jupiter Trojans, hasn't even started yet. Lucy is scheduled to reach the Trojan asteroid swarm starting in 2027, and virtually everything about what those distant asteroids might actually look like or contain remains a complete open mystery at this point. No spacecraft has ever visited a Jupiter Trojan before. Scientists have plenty of theoretical models to work from, but as Lucy has already demonstrated twice over, theoretical models are never quite the same thing as physical reality. The Trojans are widely believed to be among the most primitive, unaltered objects anywhere in the solar system, darker in color, rich in carbon compounds, and possibly containing organic molecules that predate the very formation of Earth itself. Some scientists believe they may have originally formed in the far outermost regions of the solar system, well beyond Neptune, before being gravitationally captured into Jupiter's orbit during a period of massive solar system restructuring billions of years ago. If that theory holds up, these objects are essentially messengers, carrying material from the most distant and ancient corners of our entire cosmic neighborhood. Lucy is scheduled to visit at least 6 separate Trojan asteroids between 2027 and 2033. The targets include objects belonging to the Euripides family, a collisional cluster of asteroids believed to share one common shattered parent body, as well as Patroclus and Menoetius, a rare, nearly equal mass binary pair, 2 similarly sized rocky bodies orbiting closely around one another. Each individual target represents something genuinely different scientifically, and each one likely carries its own distinct piece of the early solar system story. And given everything Lucy has already uncovered at what were meant to be entirely unimportant warm-up stops along the way, the broader scientific community is now paying extremely close attention to whatever comes next. The principal investigator behind the Lucy mission is Dr. Hal Levison, based at the Southwest Research Institute in Boulder, Colorado. Following the Donald Johansson flyby, he offered a comment worth repeating in full. He noted that these warm-up asteroids were proving to be quite interesting in their own right. That has to be the scientific understatement of the entire decade. These targets were never supposed to be interesting in any meaningful sense. They were supposed to be simple rehearsals. And yet both of them produced discoveries that will almost certainly be cited in scientific literature for decades to come. There's something genuinely deeper worth sitting with here. We currently live in an era where space exploration is faster, more capable, and more scientifically productive than at any previous point in human history. Spacecraft keep getting smaller and more efficient, scientific instruments keep growing more sensitive, and the computers processing all of this incoming data are more powerful than anything available during the original space age decades ago. And yet, again and again, whenever we actually travel somewhere new and look closely enough, the universe manages to surprise us anyway. Not in small, trivial ways either, in genuinely fundamental ways. Objects that seemed thoroughly boring at first glance turn out to be fascinating once examined closely. Rocks we assumed were simple turn out to be staggeringly complex under real scrutiny. The solar system keeps proving to be stranger than our existing models predicted it should be. This is exactly why missions like Lucy genuinely matter. This is why investing billions of dollars into sending a spacecraft on a 12-year, 4 billion mile journey across the solar system makes real scientific sense. Not because we already know precisely what we're going to find out there, but precisely because we don't. Every single time humanity has pointed a scientific instrument at something new and gotten close enough to actually see it clearly, the resulting answer has turned out to be more complicated and more genuinely interesting than the original question we set out to ask in the first place. Lucy is now pointing its instruments at things no spacecraft has ever reached before, in a region of the solar system nobody has ever previously visited, examining objects that have been sitting quietly in the dark and the cold for billions of years, essentially unchanged, patiently waiting. And based on everything already discovered so far, based on the impossible double moon, the wobbling peanut-shaped rock that defies existing models, the ancient water chemistry frozen inside iron-rich clay on the surface of a rock born out of catastrophe just 155 million years ago, based on all of that combined evidence, the smart money says that when Lucy finally reaches a rock barely half a mile wide, sitting in the middle of the asteroid belt, just told us that liquid water genuinely existed inside it at some point. That shouldn't really happen. It's too small, it's too young, it's sitting in the wrong part of the solar system entirely. And yet, the underlying chemistry is right there, locked directly into iron-rich clay on its surface, undeniable and simply waiting to be properly understood. That's exactly the kind of discovery that ends up rewriting textbooks. That's exactly the kind of discovery that makes working scientists question their existing assumptions and rebuild their models completely from scratch. And that, in the end, is precisely what great science actually looks like. Not a comfortable confirmation of what we already believed going in, but a door swinging wide open onto something genuinely unexpected. Lucy is on its way. The Trojans are waiting patiently out there in the dark, and whatever is out there has never once been seen by human eyes before. Stay curious, because the universe is far stranger than most of us tend to think. And right now, NASA is flying directly toward the strangest part of it yet.